Okay, so in this video, we're going to continue our discussion with stationary phases and how components interact with them. So we said that if our components are polar, that's great news because we can talk about polarity all day long and sound so smart, acting like our general chemistry and organic chemistry classes taught us something. Okay, well, I can go a little bit deeper than that because polarity is not the only thing that we need to account for. That means that if a compound is polar, it doesn't necessarily mean that it is the bottom of the totem pole when it develops in the tank. That means that it hardly ever moves. Sure, it's going to slow down. Absolutely, it will be toward the lower end of the plate. That is not a big deal. I'm not saying that it's not. But there are chances that there's more at play than just polarity. And out of this kind of description comes different types of bonding and pHs that we now kind of are aware of. So the hydrogen bonding, the dipole-dipole interactions, the London dispersion interactions, all of these are a thing and all of those are present, absolutely. And that is something that we need to take into consideration. All right, well, in this kind of video, we're going to take another step here and we're going to add on number 6. And number 6 is the solubility, and that solubility is in the mobile phase that we are using. So that is also a thing, and they are almost coming hand in hand. So like dissolves like, absolutely. So if I've got a component and that component is onto my plate and I need to give it mobile phase and I need that mobile phase to push through the stationary phase and I need it to separate things for me, absolutely, that is wonderful. That's what we want. But the solubility in that mobile phase is drastically important. So if it is very soluble in the mobile phase, then of course it's going to travel a little bit further. It still might have some interactions with the stationary phase. It still might hang out, just not for long periods of time. It likes that mobile phase maybe a little bit more. That is determining in solubility. So as it is more soluble in that mobile phase, it stays in the mobile phase longer and it travels up the stationary phase or through the stationary phase much faster. So solubility is going to be a thing, and that's going to be number 6 on our list, because if it's not soluble in the mobile phase, then folks, chances are it can't even move. So if it just drastically super hates the mobile phase, even if it hates the stationary phase, if it just super hates that mobile phase and it was like, absolutely not, I will never get in a car with you ever again. Don't you ever come into my life. Never want to see you again. If it ends in that type of situation, then it will never get in the car. It will never leave the stationary phase. It will just stay over at the stationary phase's house, even if they don't get along, even if they argue about their finances and their children and their work all day, every day. It does not matter. They will still stay in the house together and make each other miserable. So with that said, solubility is going to play a role. So these components do need to be soluble in some form or fashion. They need to interact with the mobile phase. They need to carry in the mobile phase a little bit, and that really is going to drive home the idea that solubility is going to be pretty important. All right, so pH, solubility now is something else that I need to take into consideration. And we get this idea that more than one thing now is at play when it concerns the stationary phases. As these stationary phases begin to do their job, well, that's great. That's good news. And we've talked about different modifications that can happen on them. And this is where those different modifications are going to come in handy. So I can now begin to play with the stationary phase. Is that component staying in a shack in the middle of the mountains? Or is that component staying in a luxury, $18 million resort style home at the beach down in the Keys? Well, the Keys don't even have a beach, but you get what I mean. Okay, so this is kind of the thing that goes on with the mobile phase and the stationary phase. And there's some terminology here that I want to talk about a little bit. The first one is something that we call normal phase, and that normal phase means or is abbreviated with an N and a P. So that NP is normal phase, and when we talk about normal phase, Folks, this is just straight up silica. That's what that is. So SiO2, 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 polar bear. So that is normally what we run. It's normally what we see. It doesn't have to be that every single time, but I would say that the majority of the times that we're running samples, they are built on the purpose of a silica-based plate that is pretty much silica with an OH group, so very polar. That is what we call normal phase chromatography with HPTLC and TLC. That normal phase is going to carry through the other, maybe like HPLC as well, and we'll see that coming back, and that at that point we'll realize, does it mean the same thing or not? But right now we're only focused with TLC, thin layer chromatography. That's where this is all about. When we begin to modify the groups and I take off the OH groups, now what can happen is that we flip the script. Flip it and reverse it, Missy. So when we flip it and reverse it, that is going to be labeled as RP, or reverse phase. So in the HPTLC world or the TLC world, what goes on is that we will be reading a method. And when we read a method in this field, if it does not specifically say otherwise, we're going to assume it is silica. That is the stationary phase on the plate. Well, all of these other ones that we talked about, C2s and C8s and C18s, all of those are very nonpolar. All of those have flipped it and reversed it. All of those are going to be reverse phase. So very often we kind of let you know, hey, there's something special here. And that something special is that we've flipped the silicas. And when we flipped the silicas, we've now flipped the script, Missy. And now we can start playing off of nonpolar interactions versus polar interactions. And for that reason, they will often be like, okay, today we are going to be running on an RP plate that is RP blah, 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 blah. So they will normally say RP2s or RP8s or RP18s to let you know that this is something a little bit out of the ordinary. The 2 means for 2 carbons, the 8 RP8s mean 8 carbons, and the RP18s, guess what, means 18 carbons. That's what that is all about. All right, so all of this is the idea that we have flipped the polarity of the plate and things begin to separate quite differently for us when we begin to develop them and when we try to separate them using this type of chromatography system. The silica gels, notice OH group, the amino NH2, the cyano in CN. Diols, di means 2, so 2 OH groups in a way. These are polar and these are middle polar, so there's polarity that's associated with it. Just not as strong, but the polarity is still there. And then straight up polar is our normal phase separation that begins to happen on the plate. And then middle polar, depending on how we play our cards, could be RP or NP or both. So those are different types of situations that we can kind of make it fit and customized to our needs on how we're trying to separate components inside of a sample as we begin our chromatography experience together. Please keep in mind that separation is going to happen with adsorption. So this is something that we talked about in the previous lecture module. Adsorption, AD, not ABs. AB is absorption. That's the blob. That's you blobbing around and eating all the people that you can find, because that's what was going on in the Blob movie. And it was just getting bigger and bigger and bigger. This is not absorption. This is adsorption. So it's sticking to the surface. That is what this means. And that is a review from the very first lecture module that we've had together. This is an example of what you're seeing on the screen of the traditional types of separation and the order of elution that we will very often see in chromatography when we use silica, which is SiO2, very polar. So what we're going to see here is that acids will tend to kind of hang out toward the bottom. Acids are very, very strongly charged, or can be strongly charged. We do see positives on them quite often. They are very polar due to how they're built, and because of that, they hang out with the silica extremely extremely well. And then as I go up the strip that is supposed to represent a plate, then I see hydrocarbons up here toward the top. And hydrocarbons are just carbon and hydrogen based systems. So they will often put like carbon in with H2N plus 2, even though that's not necessarily happening every single time. But it gives you the idea of what a hydrocarbon is. So a hydrocarbon would just be all straight up carbons and hydrogens, no bells and whistles, no functional groups, no multiple bonds, nothing kind of special that makes it stand out from the crowd. Just carbon chains with some hydrogens on them. That's what those are. So things like methane and ethane and propane and butane and pentane, all of those are straight up hydrocarbons. And of course, there's thousands of these things, right? Okay, so with that said, that is straight up carbon, straight up hydrogen, very, very non-polar, not going to be interacting with the silica at all because silica is polar. So they're going to hate the silica. They're not going to get along, and they're going to try to get away from the silica as much as possible if it can. And that's why it travels the fastest up the plate, or the fastest through a column, if this was actually a column, in order to get rid of it. Some of the other kind of common functional groups are going to be here in the middle. Alcohols, of course, we're playing off of straight up OH groups. Carbonyls are C double bond O's, but those carbonyls are flanked by R groups, which are random groups to the left and to the right. So that covers up that oxygen. It covers up the free pairs of electrons a little bit more. So it's not as strong as like a full-blown oxygen in an OH group. The free pairs are there. The free pairs are present. They're no different than anything else. They're just covered up by all of the other things that surround it in the carbonyl family. Next up are esters. So esters are a C double bond O with an O group that's like this. So once more, we get these random groups on the left and to the right, and those random groups do cover up the oxygens just like they did in carbonyls. But the difference here is that with the esters, there's an extra little oxygen. So that extra little oxygen is going to be extra little pairs that we're going to see that's going to be present. And it doesn't quite kind of cover them up as much. But the thing here is that the R groups are going to start taking over. And this carbon that was in a double bond, this is getting shared, absolutely. And then we get free pairs that are here and we get free pairs that are there. Absolutely, that's what's going on. So very similar to the carbonyls, but what's happening is that these electrons are delocalized and they can move. So they're actually going to start kind of surrounding this whole area and moving, and they're not really stuck in one spot. And if they're not stuck in one spot, then we don't quite get full-blown charges like we get, or strong polar pieces that we get in some of the other functional groups. So the R groups surround it and the R groups block it. Sure, absolutely. And then there's delocalization that's happening, and these electrons are spreading and they're moving thin throughout that entire functional group region. And because of all of this, what we're seeing is that our butter has been spread too thin. That's how I'm going to say it. So it is too thin, and it's more non-polar than it is polar, and hence it travels up the plate a little bit faster. Ethers are these RORs. That is an ether group. Again, the alkyl groups cover up that oxygen quite well, and because of that, it is more non-polar versus polar, and they normally travel a little bit further up the plate, again, because of that reason. So these are just kind of common situations that we can put a little bit of organic to it, absolutely. And we can go deeper and deeper into that, but again, it's not an organic course. I'm not going to go that route. We're just going to be talking about the instrumentation, but we need some basics. We need some foundation understanding of why things are separating the way that they are. Here's just a different type of version of what we're seeing in the last slide, and this just includes a little bit more functional group, and it actually kind of flips this whole thing in a roundabout way as far as how it describes polarity. However, with that said, look at this. Acids and bases are down here at the bottom. Saturated hydrocarbons are up here at the top. Ethers are there. Esters are there. And then ketones and aldehydes. Notice in the last slide, they just said carbonyls, C double bond O's. The amines they've added, the amines are NH2 groups. Alcohols were there in the last one. Acids and bases were in the last ones. and halides. Halides are all of our halogens. So this would be our fluoride and our chloride and our bromide and our iodide and so forth. So this is no different than the other slide. It just presents it in a different way. I think the other one's a little bit more visual. I like that one a little bit better. It just doesn't include as many of the functional groups as this one does. Do I expect you to know, like, okay, well, which one's going to travel further? No, I don't want you to memorize that list, but I do need you to understand of what's making it go up to that point. So what is in that functional group? Why is it doing what it's doing? And the concept here is polarity and the way that it interacts with the silica and that stationary phase, plus all of the other logistics that follow. So the hydrogen bonding and the dipole-dipole interactions and so forth. So that's kind of what this is going to be all about. In the next video, we're going to pick up from here, and we're going to talk about some abbreviations and what things mean, and some of the important things I need to take away off of a silica plate. That box that it comes in, there's a label on it. So what are some important pieces that I need to take away as far as abbreviations go? So that's coming up next. Get back and see me.